Hi students, Chemical Kim again, and I'm going to do a quick video lesson on doing some practice problems from Unit 8 on gas laws. To do this with me, of course you want to have Unit 8 practice problems out, a calculator, and then also the gas law equation sheet. I'm going to focus on the gas laws that I have circled here on the equation sheet, and we'll do some examples from a couple of these. So starting off, I'm not going to do all the practice problems, but I'm just going to pick some from each section. And the first is on the combined gas law. So the combined gas law, as a reminder, looks like this. P1 V1 over T1 is equal to P2 V2 over T2. And you know you have a combined gas law calculation when you have two sets of conditions given, as we see in number 18. So in number 18, we see that a diver has a set tank pressure at 770, and I'm going to highlight that can be helpful, torr at 20 degrees Celsius. So there's one set of conditions right there. And if the water pressure changes to now a second set of conditions, 746.2 torr, what is the temperature? So we're trying to find the new temperature at that new pressure. And volume is constant. To do the calculation though, before I go to set this up, I just want to show you what I like to do with this combined gas law algebraically that really helps me in the calculation. I'll cross multiply it. So the equation is going to look like this. P1 V1 T2 is equal to P2 V2 T1. So all I did was just cross multiply that equation and I can work with it. The other thing that I want to point out is that if I have something constant in the question, then I can remove it. So in this case, because volume is constant, I can actually just erase the volume out of that equation. Okay. The other thing that I like to do before I put it into the combined gas law equation is just check for everything. So I know it looks like a lot of work, but I like to say, okay, P1, V1 I don't need because it's constant, and T1, and make sure my units match. So P1 is 770.25 torr, and I'll write the unit there. T1 is 20 degrees Celsius. Now I'm going to add that to 273 to get it into Kelvin, because the important thing with gas laws is you do want your temperatures in Kelvin. So we're going to write that as 293, and just for sakes of significance, let's just say that there was a significance at that one place with the 20 degrees Celsius. So I can carry the number to 293 Kelvin. And then my second set of conditions, my P2 is given at 745.6 torr. And then my T2 is what I don't know. So I'm solving for the second temperature. Okay. So looking at my equation that I'm going to be working with, and I'll write that again to work on rearranging it algebraically. I have P1 T2 is equal to P2 T1. Now, a little trick that I do with these gas laws, having them written like this, especially the combined gas law, I'm going to circle what I'm trying to find. So in this case, I'm going to circle the T2. And then whatever is with T2, I cross off and I stick it underneath the other side. Now, hopefully algebraically, you can see what I really did was just divide both sides of the equation by P1. But this can be a trick also. So you circle what you're trying to find, cross off what's with it, and then you have the equation to plug into. So to calculate this, I'm going to take my P2, which is 745.6. I'm going to multiply that times T1 in Kelvin, which is the 293, and then I'm going to divide that by the P1, which is the 770.25. The other thing I need to note and make mention is that my pressures do match, so I don't need to convert them to atmospheres or torr, or they're already in torr, but in kilopascals. I can leave them right there as that pressure unit. So plugging this into the calculator, 745.6, and then I'm going to multiply that times 293, and then I'm going to divide that by 770.25. And I get an answer of, in my calculator, 283 0.6 or 284. So I get an answer of 284. Now the question, that's a temperature. Is that answer in Kelvin or is it in Celsius? Well, seeing how my original temperature that went into this calculation was Kelvin, this answer is also Kelvin. If I do want this answer in degrees Celsius, I would then have to subtract from the 284, I would have to subtract the 273. And so 284 minus 273, and I get an answer of 11 degrees Celsius. So just recognize with gas laws that you have to have the temperature in Kelvin when they go into the gas law, and then if you want to take it out of Kelvin, you have to subtract 273. Okay, so that's a combined gas law example. Let's go to the next page and let's do an ideal gas law calculation. Now on the gas law cheat sheet, the ideal gas law that I'm working with is that PV equals nRT. And if you look at the work that I've presented previous in Unit 8, I show and explain in the book and on video how this equation is derived from the combined gas law. So the gas laws are all very much connected. So mathematically, if you wanted to look at it like that. But anyway, I'm given one set of conditions. So I'm going to use the one set of conditions that I'm given. So I'm given a pressure of 745 torr, and I'm given a volume of 455 milliliters, and I'm given a temperature of 24 degrees Celsius. Okay, and if it is the ideal gas law I'm working with, which is PV equals nRT, then I have to see, do I have an N, which is moles? Well, no. And the question is asking for grams. And we've worked with moles and grams so much this semester that hopefully you know at this point that if you're solving for N, which is moles, you can also determine grams if you know what the gas is. And in this case, we of course know the gas is oxygen. Okay, so just so you recognize that. And then R is the gas constant, which is this 0.0821, which I do explain in a previous video and also in the unit book of how that number is derived. That number could be derived with other units, but that's the gas law unit that we're going to use. Because we're going to use that gas law unit, I have to match my pressure to atmospheres. So torr, I'm going to convert torr to atmospheres, and I do that by dividing by 760. So I'm going to take my 745 divided by 760, and I get 0.980 atmospheres. So that's my pressure. In the ideal gas law, that R value for, now let's look at volume, is liters, not milliliters. So I do need to have my volume as 0.455 liters before I put it into the equation. And just like previous, I need my temperature in Celsius. I mean in Kelvin from Celsius. So I'm going to take my 24 plus 273, and I have a 297 Kelvin. Okay, so I have everything but N. I'm going to be solving for N, and then I can convert moles to grams. Okay, so PV equals nRT. Just like I showed previous, I'm going to circle my N. I'm going to cross off RT and stick it underneath the other side. And that's what I'm plugging into. So I'm going to take my pressure, 0.980, and I'm going to take my volume, 0.455, and I'm going to divide that by the R, 0.0821, and then I'm going to multiply that times the T, the 297. So let's plug that into the calculator. So starting my parentheses, 0.980 times 0.455, close my parenthesis, divide, start my parenthesis, 0.0821 times 297, close my parenthesis. And I get this very small mole number, okay, and that would be, and I'll carry it to three significant figures, 0.0183 moles, and the gas that I'm working with is O2. Okay, so what do I do now? The question is asking for grams, so I simply use the molar mass of oxygen. Now keep in mind, oxygen, you see how I wrote that as an O2 as a diatomic. So I'm going to use the molar mass 32. Where do I get the molar mass from? of course, the periodic table. When you look at the periodic table, in oxygen, its relative atomic mass, or its average atomic mass, is 15.9994, but I'm going to round that up to 16.0 times 2. So I use the molar mass of 32. So I'll set that problem up. So I'm going to take my 0.0183 moles of O2, and I'm going to multiply by the molar mass of oxygen, which is 32. So I'll take my answer that's on the calculator times 32, and I get a gram value for this gas of 0.585 grams of oxygen. And that's it. So this is using the PV equals nRT given one set of conditions. The R is a gas constant, which is really derived from the combined gas law given one of the conditions making it STP. And I kind of explained that previous, like I said. So give that a try some more on this page. But then I'm going to move to now showing you some calculations with density and molar mass. Okay, so the density and molar mass equations here, as I previously explained in Unit 8 and showed in the book, these equations are also derived from the ideal gas law. So I let you know this because in these calculations you could actually use the combined gas law, the ideal gas law, to do the calculations, but I just find it's easier to plug them right into these equations. So let's take a look at that. What's important to also know is what everything what everything stands for in these equations. So let's look at this molar mass equation. I have a little key here that kind of helps out, but that is my molar mass, the mm, and then this little m is the mass that I indicate there. So that's what that stands for. R, of course, is the 0.0821. T is temperature, P is pressure, V is volume. On this molar mass equation, the only thing new there is D, which stands for density. And then on the density equation, again, that mm stands for molar mass. So we can work with these equations and do some calculation. I'm going to do number 53, and I like 53 because it looks like you really are not given any numbers, but you actually are. And let's talk about it. Let's see what we're looking at. What is the density? So if it's asking for density, I probably want to use that density equation, which is molar mass P over RT. So again, I got that from the gas law equation right there. Molar mass P times RT. And mm stands for molar mass, right? So let's go back to the question. And we know we're trying to find density. Before I plug everything in, let me try and decide, do I have a molar mass? Well, of course, I have the gas, and the gas is nitrogen. And remember, just like I showed you with the one example previous, it's a diatomic, so we're working with N2. So we would be using the molar mass for nitrogen, and I'll bring it up from the periodic table. Nitrogen here is 14.01. I'm going to multiply that times 2 because it's a diatomic. So I'm going to use 28.02 grams per mole for the molar mass. Okay? And then pressure is, well, I don't see any number, but I do see this STP. And if you got a little stuck, again, go back to that gas law equation sheet, and you'll see on the gas law equation sheet that I do indicate that if my gas, it froze on me here, but if you look at the top of the gas law equation sheet, you will see that I have the conditions of STP, which temperature is 0 degrees Celsius and pressure is 1 atmosphere. Okay, so my pressure is 1 atmosphere, and my R, I already know, is the 0.0821 atmospheres, liters per mole K, and again we want to make sure our units match R. And then the last is the temperature, and temperature at STP is 0 degrees Celsius or 273.15 Kelvin. So we do have all the values we need to plug into this calculation. So I'm going to put those numbers in, and I'm not going to put the units in, but I'll talk about how the units cancel and then what units we'll have for the answer. So molar mass is 28.02. Pressure is 1 atmosphere. And remember, these are standard pressures, so I'm not going to use that for significant figures. That's an STP. And then R is the 0.0821, and then temperature is the 273.15. So I'm going to plug that into the calculator. So I'm going to take 28.02 times 1, of course, is 1, divided by, start my parenthesis, 0.0821 times 273.15, close my parenthesis, and I get 14.7. Now that number might look high because hopefully you know gas density should be lower than solids and liquids, but let's look at the unit, and it actually is a very low density. So if we look at our R value in the atmosphere, so the atmosphere unit's going to cancel from the pressure unit, and then our Kelvin unit will cancel with the temperature, and then our mole unit will cancel with the molar mass. So what we are left is the unit gram per liter. And we often list gases with that unit because they are so low in density, so we don't have to write a really small number. Because solids and liquids, we tend to use gram per milliliter or gram per centimeter cubed. So it sort of as a comparison. The very last one that we're going to work on here, number 57, states let's calculate the molecular mass of 4.5 grams of a gas. Let me get the whole question here. At a volume of 345 milliliters and a pressure of 45.8 psi. Okay, so we're going to set this up using the molar mass calculation. Now in the molar mass calculation, you see that there are two choices of molar mass equations. Since density is not given, I'm not going to use that density equation. Mass is given, so I'm going to use this molar mass calculation. So hopefully you can see based on what you're given which equation to use. So we're going to do molar mass is equal to mass RT divided by PV. And I'm just going to plug the values in and hopefully see that our units are going to match and cancel out as we go. So the mass that's given is 4.5 grams. The R value is the 0.0821, and that would be atmospheres liters per mole K. The temperature value that's given, and that value is given in, let's see, 25 degrees Celsius. So we're going to change that to Kelvin to 297 Kelvin, and then divided by, moving that over, pressure, which is 45.8 psi. Now for this one, I will have to convert my pressure from psi to atmosphere. So I'm going to take 45.8 divided by 14.7 for the conversion. So I have 3.12 atmospheres, and then the last, of course, is going to be, well, it's going to be volume, and that's the 0.345 liters. So we're going to calculate all that out. So I'm going to start with my parenthesis, 4.5 times 0.0821 times 297, close my parenthesis. Oops, I see I made an error, so let's do that again. So we're going to take 4.5 times 0.0821 times 297, close my parenthesis, and then hit divide, start my parenthesis, 3.12 times 0.345, close the parenthesis, and we get 101.9. And with units canceling, we see that our Kelvin unit cancels, our liter unit cancels, our atmosphere units cancel, so we're left with gram per mole, which is molar mass. And that's it.